Hi students, good evening to every one of you. Yeah, your future doctors. Last class we discussed about chemical bonding. Right. Now, today we are going to discuss about how to decide the geometrical shape of covalent molecule. To explain the geometrical shape of covalent molecule, different scientists proposed different theories. For the first time, a theory was proposed that is called valence bond theory. Valence bond theory. It's called VBT theory, valence bond theory. This theory is proposed for what purpose? To explain the geometrical shape of the covalent molecule. According to this theory, a covalent bond is formed by overlapping of atomic orbitals. The atomic orbitals which having similar energy and which having similar symmetry or overlap. When these are overlapped, that results covalent bond. That is, the overlapping atomic orbitals must have similar energy and similar symmetry. Right. The extent of overlapping. The extent of overlapping of atomic orbitals decides the strength of the covalent bond. Decides the strength of the covalent bond. The strength of the covalent bond is decided by extent of overlapping of atomic orbitals. That means, if the two atomic orbitals are overlapped maximum, because of maximum overlapping, that results a strong covalent bond. A strong covalent bond is formed. The extent of overlapping between the two atomic orbitals is minimum. Minimum overlapping of atomic orbitals, that results a weak covalent bond. Right? The formed covalent bond is a weak bond or a strong covalent bond. How can you decide? That is decided by extent of overlapping of atomic orbitals, magnitude of overlapping of atomic orbitals. If the atomic orbitals are overlapped at minimum, that forms a weak covalent bond. If these are overlapped at maximum overlapping, then that forms a strong covalent bond. Right? Next. The geometrical shape of the covalent molecule is decided by the geometry of the molecule. The geometry of the covalent molecule is decided by direction of overlapping of atomic orbitals. Direction of overlapping of atomic orbitals. Direction of overlapping of atomic orbitals. That means on which direction the atomic orbitals get overlapped. On the same direction, arrangement of atoms is take place that will decide particular geometry of the molecule. Right? If the atomic orbitals are overlapped in a linear manner, then they form linear geometry. If the atomic orbitals are overlapped, the overlapping atomic orbitals are in the form of a trigonal planar manner, that will decide the trigonal planar geometry. That means the geometry of the molecule is decided by direction of overlapping of atomic orbitals. The strength of the covalent bond is decided by extent of overlapping of atomic orbitals. Extent of overlapping decides the strength of covalent bond. Direction of overlapping, on which direction the atomic orbitals get overlapped, that will decide the geometrical shape of the covalent bond, right? Then, according to this theory, a covalent bond is formed by overlapping of atomic orbitals. Which atomic orbitals? Will all atomic orbitals present in the atom? No. In an atom, those atomic orbitals which are present in the valence cell, outermost cell, that are only participate in overlapping to decide the particular geometry of the covalent molecule. That means only valence cell atomic orbitals are participate in overlapping. Valence cell atomic orbitals are participate in overlapping. Maybe all valence cell atomic orbitals? No. Those valence cell atomic orbitals which having unpaired electrons. You know, the atomic orbitals, SPD of atomic orbitals, they have paired electrons. These atomic orbitals cannot participate in overlapping. The participating atomic orbital must have single electron, unpaired electron, half-filled valence atomic orbitals only participate in overlapping to form what? Covalent bond. That means half-filled atomic orbitals which are present in the valence cell, outermost cell of an atom, or participate in overlapping, that results a covalent bond is formed. Covalent bond is formed by overlapping of atomic orbitals present in the valence cell, which must be half-filled. Each and every point is important. Each and every word is important. Okay, so overlapping of atomic orbitals present in the valence cell, which must be half-filled, or produces covalent bond, right? Next, overlapping of atomic orbitals are of different types. If the two atoms, S and S atomic orbitals are overlapped, then they form SS overlapping. S orbitals are spherical in shape. That's why the probability of finding the electron is equal in all the directions. That's why they form a sigma SS bond. Sigma SS bond, right? Because these are overlapped along the internuclear axis. Axial overlapping. Right. So S atomic orbital of one atom, S atomic orbital of another atom are overlapped axially. They form sigma SS bond. Right. If S atomic orbital of one atom and P atomic orbital of another atom are overlapped, they form sp covalent bond. If P atomic orbitals of one atom and P atomic orbital of another atom are overlapped, they form pp bond. Right. So overlapping is different types. That is, if two half-filled S atomic orbitals present in the valence cell, two half-filled atomic orbitals of the two atoms present in the valence cell of an atom are overlapped, they form SS bond. S atomic orbital of one atom having half-filled electrons, p atomic orbital of another atom having half-filled electrons or get overlap, then they form sp bond. P atomic orbital of one atom having half-filled electrons, p atomic orbital of another atom also having half-filled electrons. It is the both atoms, the p atomic orbitals which are half-filled, the half-filled p atomic orbitals of the both atoms are overlapped, then they form pp bond. Right. If p atomic orbital of one atom and d atomic orbital of another atom which are having half-filled electrons get overlapped, then they form pd bond. That is pt bond, right? So that means overlapping is of different types. There is types of overlapping of atomic orbitals. Is SS overlapping, will get SS bond. SP overlapping, will get SP bond. PP overlapping, will get PP bond. Or PD overlapping, will get PD bond. Right. Next one. The overlapping of atomic orbitals is of two types. All atomic orbitals of an atom are not overlapped in the same manner. So the overlapping is of two types. The atomic orbitals which are get overlapping of atomic orbitals in two ways. The two methods of overlapping is possible. One is the atomic orbitals of the two atoms are overlapped along the internuclear axis, axial overlapping. So what is internuclear axis? So for example, so this is a one p atomic orbital of one atom A, and the p atomic orbital of another atom, that is atom B. So these two are get overlapped. This is the place where they get overlapping, right? Because of that, so there they exchange the electrons here. The half-filled electron of this and half-filled electron of this are get exchanged. Then that forms results in covalent bond. Covalent bond is formed, right? Now here, what happened is these two atomic orbitals, the two atomic orbitals are overlapped axially. Because of axial overlapping, then a bond is formed. So here this axial overlapping we also call it as along the internuclear axis. Axial overlapping we also call as overlapping of two atomic orbitals along the internuclear axis. What is internuclear axis? It is the nucleus of atom A, the nucleus of atom B, right? Inter means in between the nucleus. That is internuclear axis. The imaginary line will not exactly not existing there, just for understanding the imaginary line which is passing through the nucleus of both the atoms. That line we call as internuclear axis. Inter means between the nucleus. The imaginary line that is passed through the nucleus, in between the nucleus of both the atoms. The line is passing in between, in between the nucleus of both the atoms. The imaginary line that is passed, the line we call as internuclear axis. That is nothing but axial overlapping or overlapping of atomic orbitals along the internuclear axis. That's what axial overlapping. That means if the two atomic orbitals are overlapping axially, the two atomic which are half-filled. Wherever I am explaining this entire concept of this half-filled atomic orbitals, keep it on mind, right? So the half-filled atomic orbitals of the two atoms, that is two atomic orbitals, the two atoms are overlapped axially. Then they form a sigma covalent bond, simply we call as sigma bond. So how sigma bond is formed? By axial overlapping of atomic orbitals of the two atoms. The two atomic orbitals of the two atoms which are half-filled are overlapping laterally. This is lateral overlapping. So here, this is the area where they get overlapped. So this is the two atomic orbitals, two atoms are get overlapped like this. So then you will get a sigma covalent one is from along the internuclear axis. They are overlapping. This is overlapping, right? The two atomic orbitals, the two atoms The two atomic orbitals, the two atoms are overlap laterally like this. Lateral overlap, sideways overlap, sideways overlap, sideways. You can't see this one, right? Overlap, right? This is called, they form pi covalent bond, simply called pi bond. So axial overlapping, this is sigma bond. Lateral or sideways overlapping, pi bond is formed, right? So here there is overlapping of atomic orbitals in two ways. So the atomic orbitals, the half-filled atomic orbitals of the two atoms may be overlapped axially, that forms sigma bond, and the two atomic orbitals which are half-filled are overlapped laterally or sideways manner. Lateral overlapping or sideways manner. Then that form what? That results pi bond. Pi covalent bond simply called pi bond, right? So in case of axial overlap, if the two are overlap like this, then here the electron cloud after overlapping they exchange the electrons, right? So this is a one orbital, this is a half filled, we have one electron, right? And another orbital also having one electron, right? These are get participated, right? And now these two electrons are shared with the two atoms. Now these electrons belong to this one also. Their electrons are negative. Nucleus is positive. They get attracted. And here also electrons are negative. This nucleus is positive. They get attracted. So after overlapping, you get the structure is like this. The overlap orbitals are like this. Here, this is the nucleus of this one, and the electrons are freely rotated with the nucleus of both the atoms. After overlapping, the electrons are freely rotated. They will here also, that freely rotated. Free rotation is possible because of overlapping along the internuclear axis. That's why sigma bond is a strong covalent bond. Why is sigma bond strong covalent bond means? Because along the internuclear axis, maximum overlapping is possible. That results in strong covalent bond. But later side overlapping, maximum is not at all possible. That's why a weak covalent bond. So pi bond is a weak bond, sigma bond is a strong bond. Why? Because maximum overlapping is possible in sigma bond, and maximum overlapping is not possible here. Minimum overlapping of that results pi bond. Then in sigma bond, here the electron cloud is located, is concentrated along the internuclear axis. Here, along the internuclear axis, the electron cloud, these are the electron cloud, right? The electron cloud is concentrated there along the internuclear axis, right? But in pi bonds, the electron cloud is concentrated above. Here overlapping is taking place above and below the internuclear axis. Electron cloud that is perpendicular to internuclear axis, right? So in case of pi bond, the electron cloud is, because they are overlapping here, right? That's why the electron cloud is concentrated above and below the internuclear axis. This is the internuclear axis, perpendicular to the internuclear axis, right? Next one. In sigma bond, the electrons are freely rotated. Free rotation is possible, but in pi bond, free rotation is not possible because here axis is there. It's stuck here, right? Not possible complete rotation. So pi electrons free rotation is not possible, right? Next, any type of atomic orbitals can form sigma bond. Maybe yes, P, any. Okay, any atomic orbitals can form sigma bond, and also hybrid orbitals are also form sigma bond. All types of atomic orbitals overlapping and overlapping of hybrid orbitals with atomic orbitals also produce sigma bond. But here pi bond, right? So pi bond can form atomic orbitals are overlap, all type of atomic orbitals, and hybrid orbitals only can form pi bond. Hybrid orbitals never form sigma bond. Okay, that means sigma bond is formed by only pure atomic orbitals, which are not participating in intermixing, which are not hybridized. Okay, that is called unhybridized orbitals or pure atomic orbitals, which are within the atom. That atomic orbitals only undergoes sigma bond formation. But the pi bond is formed by pure atomic orbitals and also hybrid orbitals, atomic orbitals SPDF and also hybrid orbital, this sp, sp2, sp3, these are all also false pi bond, right? So these are the main points you have to keep in our mind, right? That is, so this is sigma bond is a strong bond. Why? Because here maximum overlapping is possible, and pi bond is a weak bond. Okay, yeah. So pi bond is a weak bond. Why? Because here minimum overlapping is possible sideways manner. Okay. So maximum overlapping is possible along the internal factors axially. Right. Next, the sigma bond is here the electron cloud is concentrated. The electron cloud is concentrated along the internuclear axis. Along the internuclear axis. But here the electron cloud is concentrated. The electron cloud is concentrated or present above and below the internuclear axis. Above and below the internuclear axis. Here, the electrons free rotation is possible. Free rotation of sigma bond electrons is possible between the nucleus of both atoms. But here, free rotation of electrons free rotation is not possible. That is, pi electrons are not rotated freely. Free rotation is not possible, not rotated freely. Free rotation is not possible because electron cloud is above and below. Right. Next, sigma bond is formed by all types of atomic orbitals. That is S, P, D atomic orbitals. And pi bond is formed by atomic orbitals and also hybrid orbitals. Atomic orbitals and also hybrid orbitals. Okay, so pi bond is formed by this atomic orbitals and also hybrid orbitals forms pi bond, right? Got it? Yeah. Next one. For example, if you want to overlap S atomic orbitals, then generally some of the homoatomic molecules, take it for example formation of H2 molecule. Now these concepts are applied. All these concepts are postulates of valence bond theory. Now by applying these concepts, now we are going to discuss about formation of different molecules by applying valence bond theory postulates. So H2 molecule here, hydrogen have 1s1 atomic orbital. So one electron is there in the s orbital. Another hydrogen also s orbital there with one electron, half filled s orbital. This spherical in shape. This hydrogen having one electron and this hydrogen having one electron. So there is the s atomic orbital of both the atoms or get overlap axially. Now the question is s atomic orbital of one atom and s atomic orbital of another atom are overlap axially. That is around the internuclear axis. Then they form sigma SS bond because both are overlapped. Okay, half filled S atomic orbitals of both the hydrogen atoms. Both are half filled, right? Of both the hydrogen atoms are overlapped axially to form sigma SS bond because both are overlapped axially overlapping. There is a sigma bond. Which atomic orbitals are overlapped? S atomic orbital of one hydrogen atom. Yes, another hydrogen. That's why you get sigma SS bond. Next one, formation of Cl2 molecule. In Cl2 molecule, you know the atomic number is 17. The electronic configuration, that is neon, then 3s2, 3p5. 3p5 means the p orbitals, px, py are paired. Only pz is unpaired. We want only half filled or single atomic orbitals, right? So only pz atomic orbital is available for overlapping on each chlorine atom, right? So that's why half filled pz atomic orbitals of the two chlorine atoms are overlapped axially around the internuclear axis to form sigma pp bond. Sigma pp bond. because both are overlapped axially, you get like this. So this is a px atomic number of one fluorine atom and px atomic number of another fluorine atom are overlapped axially along the number axis. Then you get sigma pp bond. That is sigma pp bond. Right. Next one. Take for example HCl molecule, right? Here, hydrogen having S atomic orbital, which is half filled, and fluorine having half filled PZ atomic orbital. The half filled S atomic orbital of hydrogen atom is get overlapped with the half filled PZ atomic orbital of fluorine atom. Then both are get overlapped axially along the nuclear axis. Then they form sigma sp bond, right? Okay. So this is the way of SS, sigma SS, sigma pp, sigma sp like that. Then, if take for example, with the O2 molecule. In case of O2 molecule, so O2 molecule, yes, oxygen atom having atomic number 8, electronic configuration 1s2, 2s2, 2p4. 2p4 means here px is paired, only py and pz are unpaired or filled, right? Okay, so this is two p orbitals are half filled, right? On each carbon atom, the same other carbon on each oxygen atom, right? The other oxygen also two half filled atomic orbitals are available, right? Now, at first, one may be py or pz, anyone. So the py or maybe pz, anyone. For example, we consider as a pz. The half-filled pz atomic orbitals of two oxygen atoms are overlapped axially along the nuclear axis. Then they form a sigma bond. So this is a pz atomic orbital of one fluorine atom and pz atomic orbital of one fluorine atom are overlapped. Then you get sigma pp bond or pz bond, right? Next, another bond is also there. That is another atomic orbital is present, right? That is py, right? On each oxygen atom. Now, half filled py atomic orbitals of both oxygen atoms are overlapped laterally. These are overlapped laterally, sideways manner. Then they form pi py bond, pi pp bond. We simply call pi pp bond, right? That means here in O2 molecule it forms by overlapping of these two. It forms a sigma bond between the two oxygen atom. And the overlapping of these two, that is py py. Laterally, it forms a pi bond. That means in O2 molecule, between two oxygen atoms, two covalent bonds are present. One is sigma bond, another is pi bond. Check in our mind, students. Always between two atoms, if more than two bonds are present, it will be 2 or 3 bonds are present. Among that, only one bond is sigma bond. Remaining all other bonds are pi bonds. Okay, sigma bond is only one. Remaining all other bonds are pi bonds. Okay. That too, the first formed bond is sigma bond. Generally, the atomic numbers get overlap axially because axial overlapping is maximum is possible. That's why the first formed bond is sigma bond is the first formed bond. This is the first formed bond, and pi bond is formed after formation of the sigma bond. It is formed in nature. After formation of sigma bond between two atoms. Maximum number of sigma bonds is only one. And pi bonds may be 2 or 3, whatever, right? So that is, so here, one is sigma bond is maximum number. Maximum number of sigma bonds is only one. So pi bonds may be greater than 1, it may be 2 or 3, right? So that's why here 2 bonds, one is sigma bond, and another is pi bond, right? So these are the concepts explained on valence bond theory. But if these concepts you apply for some of the molecules, for example, if you want to know there is a methane molecule. So in case of methane molecule, here, so carbon atomic number that is 6. There is now here 1s2, 2s2, then 2p2, right? Here, the ground state, the excited state, the first excited state, one s electron transfer to p orbital. Then you will get 2s1, 2p3, 2s1, 2p3. So one s orbital is half filled. Other pyramids are also half filled, right? Now 4 atomic orbitals are half filled, all are ready to participate with the hydrogen atom. In hydrogen atom, each hydrogen atom having one half filled s atomic orbital, right? Now, so among that, first look here. One half filled s atomic orbital of carbon atom can overlap axially with the half filled s atomic orbital of hydrogen atom. Yes, sir. Here it is a s atomic orbital of carbon, which is half filled, and this is also s atomic orbital of hydrogen. Both are get overlap axially on the axis, right? So then you will get it is like this. So they get overlap like this. So this is s atomic orbital of hydrogen, and this is the s atomic orbital of carbon atom. Both are get overlap axially. Then they form sigma ss bond, sigma ss bond, right? Next one. Then remaining p orbitals are available here. P orbitals are available here. How? So that is here s orbital is available. The remaining 3 half filled p atomic orbitals of carbon atom can get overlapped axially with the 3 half filled s atomic orbitals of 3 hydrogen atoms. Axially. Then they form sigma sp bond, sigma sp bond, right? Sigma sp bond. So this is not represented. So this is one, and this are overlap. This is the s atomic orbital, and this is the atomic orbital overlap here. You'll get this one, and this is also s atomic orbital, and this is the atomic orbital. So you'll get like this. So this is ss overlapping of first one, and this is sp overlapping of second one, and this is sp overlapping of third one, and this is sp overlapping of fourth one. So all this is what this is the first one. This is the ss atomic orbital. This is exotic practically you can observe like this. Then what you get here? So this is the carbon, and this is the one bond. This is sigma ss bond, and this is the one other bond with the hydrogen. This is sigma pp bond. Okay, and this is also sigma sp bond, and this is also hydrogen sigma sp bond. So that is among the 4, one is sigma ss bond, remaining 3 are sigma sp bonds. Got it? All these are overlapped in such a way to minimize the repulsions among them. That means they are overlapped. How they are overlapped is, so this is the one sigma ss bond, and this is one sigma sp bond, and this is one sigma sp bond, and this is one sigma sp bond. So all are perpendicular to each other and this angle. So these two are perpendicular to each other. These two are perpendicular. These two are perpendicular. These two are perpendicular. According to Wales bond theory, because orbitals are arranged perpendicular to each other. You know, so there are, so what are the 3 p orbitals? Tell me. Px, py, pz. Px, py, pz. So this is px orbital, this is py orbital, this is pz orbital. So px orbital is perpendicular to py. Py is perpendicular to pz. Okay, if these are overlaps with the hydrogen atoms, you get perpendicular, right, bonds with hydrogen atom. Okay, that's why all the orbitals are perpendicular to each other. That's why in methane molecule, the bond angle is 90 degrees. According to valence bond theory. Why it is like this? Because here the orbitals are get atomic orbitals get overlapped perpendicular to each other with the s atomic orbital of hydrogen atom, right? But this 90 degrees angle of methane molecule is wrong. Experimentally, they find out that there is a methane molecule 109 degrees 28 minutes. That means this theory cannot explain the geometry and bond angle of the sum of the covalent molecules. It fails to explain because by overlapping of atomic orbitals, which are all perpendicular to each other, that are all not exactly decide the geometrical shape and bond angle. It explains the geometrical shape and bond angle of some of the molecules, good, but it fails to explain the geometry and bond angle of some of the covalent molecules. Then, to overcome these demerits, another theory is compared distance, that is called Vesper theory, right? Yeah. Okay, first. Right. And those atomic orbitals which having similar symmetry only get overlapped. Keep in mind, students, a px atomic orbital can overlap with the another px atomic orbital. It cannot possible to overlap with py. Why? Because symmetry is different. This is what px atomic orbital. This is what py atomic orbital. Both are not possible to overlap. If px can overlap with px only, if py can overlap with py only. Py cannot overlap with pz because symmetry is different. Right? This is also very important. And here pz dz square. Dz square orbital, that is in complex compounds, their overlapping is different. Okay, d orbitals overlapping is different. That is not explained by valence bond theory. Okay, their complex compounds will discuss this, right? Here not by here, right? Yes. Okay, so this we have to consider the concept S orbital and p orbitals, right? Yes. Next one, Vesper theory, valence cell, electron pair, repulsion theory. What is Vesper theory? Valence cell, electron pair, repulsion theory. Okay. This theory is proposed for what purpose? To explain geometrical shape and bond angle of some of the covalent molecules. How? That is, according to this theory, the geometrical shape and bond angle of a covalent molecule is decided by repulsions between the electron pairs present in the valence shell of an atom. That means an atom means valence shell, outermost cells. What are they? Electron pairs are present. These among the electron pairs, what happened? Repulsions are takes place. That repulsions between the electron pairs present the valence shell of an atom can determine the geometrical shape and bond angle of the molecule. This is the main concept in this theory. Hence, so-called Vesper theory. Repulsions between electron pairs present in valence shell of an atom decides the geometrical shape and bond angle of the molecule. Right. Okay. Now, what are the main postulates in this theory? According to this theory, in an atom, the electron pairs present, the total electron pairs present in the valence shell of an atom are of two types. Those all valence electrons not at all participate in bond formation. Keep in your mind. Or then generally in the bond formation, which electrons are participate? Valence electrons. All valence electrons? No. Okay. All valence electrons not at all participate in bond formation. They may or may not be participating in bond formation. Those valence electrons which are participating in bond formation are called bond pairs of electrons. Those valence electrons which are not involved in bond formation are called lone pairs of electrons. Bond pairs plus lone pairs together will get total number of electron pairs present in the valence shell of an atom. Right. Next, if a molecule in which whatever the valence electrons are present in the valence cell, if all are participating in bond formation, all bond pairs are present in the molecule, right? If a molecule, this is very important, if a molecule in which only bond pairs of electrons are present, if the molecule having only bond pairs of electrons, that molecule have regular geometrical shape and regular bond angle. There is no any deviation of geometrical shape, there is no any deviation of bond angle, right? We have normal geometry and a normal bond angle, regular geometry and regular bond angle, right? The molecule having only bond pairs of electrons, it have regular geometrical shape and regular bond angle. Regular bond angle. There is no deviation of geometry and bond angle, right? Next, if a molecule having along with the bond pairs of electrons, if they have lone pairs of electrons also, these lone pairs of electrons causes repulsions onto the bond pairs of electrons. Because of that, the molecule geometrical shape and bond angles get deviated, the bond angles get reduced, right? The molecule having both bond pairs and also lone pairs of electrons, the geometrical shape and bond angle of the molecule is get deviated, right? If a molecule having only one lone pair of electron, that lone pair causes repulsion on the bond pairs, then the deviation is very less. If the molecule having two lone pairs of electrons, here repulsions are take place between the lone pair also and lone pair bond pair also. That's why maximum repulsion is take place. That's right. Deviation of bond angle is very more. So bond angle is so much reduces. That means as number of lone pairs increases, the strength of repulsions increases, then bond angle decreases so much. Right? So that is as number, very important, number of lone pairs of electrons increases, repulsions between that is increases, repulsion forces increases among them. Because of that, bond angle is so much decreases, right? Then the order of repulsions, how much? The order of repulsions between these electron pairs. Order of repulsions between what? Between the electron pairs and the valence system. The order of repulsions. These are all present valence system on the right. Okay, some are bond pairs, some are bond. These are not totally electron pairs. The order of repulsions between the electron pairs is lone pairs repulsions is very stronger, greater, which is greater than lone pairs and bond pairs, which is greater than bond pairs and bond pairs. That means that the two bond pairs repulsions are very less, the two lone pairs repulsions are very high. Because lone pairs are bachelors, bond pairs are get married, they form a covalent bond. That's why they are happy. But lone pairs are bachelors. They are not involved in a marriage bond like a covalent bond. That's why between them, they have alone right, they have more repulsions. So that's why with the lone pairs of electrons, repulsion strength is more between the lone pair than the lone pair in bond pair, and which is greater than two bond pairs. Right. Then, if you understand the concept like this, then the subject is very easy. Not a subject, you know all these things like that. Not feel it, then you can easily understand all concepts. This is the way how to study it. You know the subject, you know all these things. Okay. Now here, what about? So if with the bond pairs also repulsions are not there, no, there. With the bond pair also repulsions are there, but minimum. Okay, minimum repulsions are there. Minimum something is there. How much there is? How much? How can you know? The strength of repulsions in the bond pair and bond pair is minimum. That is depends on the repulsions in the bond pair and bond pair is depends on repulsions between two bond pairs of electrons is depends on electronegative difference. Electronegative difference between central atom and bond atom. Between the central atom and bond atom. For example, if you take it ammonia and H2O here, So ammonia, it forms here 3 covalent bonds. These are bonded, is a lone pair. Between these 2 bond pairs also repulsions are there. This depends on electron negative difference between the nitrogen and hydrogen. And here also, in case of H2 also, 2 bond pairs, 2 locates are there. Between these 2 repulsions are there, but this is minimum. How much there is? Something is there. How much there is? I know. I want to know it. There is how much there is depends on electron negativity difference between center atom and bond atom. Right. Next one. According to this theory, if the atom or the molecule, if it having pi bonds, the pi bond is formed by lateral overlapping. These electrons are exposed to outside, but sigma electrons are there on the internal axis. These are deeply situated. Pi electrons are exposed to outside. That's why these electrons are between these repulsions are more, right? That's why here, if the molecule having that is multiple bonds, that means it having there is a double bond and also triple bond, right? So in the triple bond, that is the repulsion strength is more than the double bond, which is more than the single bond. That is the strength of repulsions in a molecule. If having multiple bonds, the strength of repulsions between the multiple bonds is so triple bond repulsions is more than the double bond, which is more than the single bond, right? So all these are main postulates explained in Westport theory. According to Westport theory, the main concept is so the geometrical shape and bond angle of a molecule is decided by what? Repulsions between the electron pairs present in the valence cell of an atom. Electron pairs in the valence cell between bond pairs or maybe lone pairs. Among them, repulsions are take place. That will decide the geometry and bond angle of the molecule. If the molecule do not have any lone pairs, only bond pairs are there. We have regular geometry, regular bond, happy with it. If the molecule have lone pair, because of that, it causes repulsions with the bond pairs. That's why the geometry and bond angle is deviates, decreases, reduces. If lone pair increases more, bond angle decreases more. Lone pair increases more, bond angle decreases more. Right? So these concepts you want to apply to discuss many molecules. For example, the Westport theory is applied first to ammonia molecule. In ammonia molecule, in case of the ammonia molecule, right? So here, so 3 hydrogens are there and one lone pair is there. So nitrogen have 5 valence electrons, right? So 1, 2, 3, 4, 5. Hydrogen have 1 electron, right? Now, so around the central atom nitrogen, how many electron pairs are there? 1, 2, 3, 4. 4 electron pairs are there around the central atom. Among that, how many bond pairs of electrons are there? Bond pairs of electrons. This 1 pair, this 1 pair, this 1 pair. So 3 bond pairs are there. Among the 4 electron pairs, all the 4 electron pairs not possible in bond formation. Only 3 electron pairs formed with the 3 covalent bonds with 3 hydrogen atoms. So bond pairs are 3. So and lone pairs of electrons is 1. So bond pairs is going to get total number of electrons 4, 3 plus 1, 4. Right? Because of this lone pair, it causes repulsions on the bond pair. Because of that, if it is also bonded, it's arranged like this. That will give the tetrahedral geometry of the molecule. But it is the lone pair. It causes repulsions on the bond pair. Because of that, the tetrahedral geometry changes to pyramidal. And the bond angle, tetrahedral bond angle is so much. 109 degrees 28 minutes. Okay, 109 degrees 28 minutes. This changes to 107 degrees 28 minutes. 109 to 107 that is decreases. Why? Because of the repulsions, right? So 10 is lower. So applications of this Westport theory explain next class. So I have to explain NH3, H2O, and same for this called. I will compare that also. So next class I'll explain comparatively. You can get an idea from these questions will appear for examinations. Previous questions are also there. Okay. So time is over. Today we stop the session. Next class will continue this one. Once again I'll explain this one from NH3. I have to compare. It will take some time. That's fine. Okay. Fine now. Yeah.